Hi everybody, Mrs. T. This is chapter 3, video 2, and we're going to do some dimensional analysis and some conversion practice. So the first thing we're going to talk about is dimensional analysis, which is used when converting one unit of measure to another unit of measure. So what we want is a way to take measurements and keep the amounts equal, but transfer from one unit of measure to another. When we do that, we're going to use equivalence statements that relate the two units, and these are going to come in forms of fractions. And we're going to derive the appropriate unit factor by looking at the direction that we want to cancel out the unwanted unit. And we're going to multiply throughout. And when we do that, that's going to get us from the units we don't want to the units that we do want. One of my favorite things about dimensional analysis is that when we can use this in real life. In my actual adult life, I use dimensional analysis. You use dimensional analysis to scale a recipe, or if you, let's say you have something that measures milliliters and the recipe is in cups, or you have something in grams and you have something that measures in ounces, weight ounces. So we can actually use this in real life as adults. Everyone always asks, when am I ever going to use this again? I actually use dimensional analysis in my regular life and not in terms of chemistry. So for example, if we want to take something in terms of feet and we want to represent it to inches, so our golf ball went 6.8 feet across the green, and we want to know how many inches this represents. 6.8 feet is our original amount. We are always going to take that amount with its unit and put it as a fraction over 1. Then we are going to multiply by a fraction where the numerator and the denominator are equal to each other in two different units. One of the units has to be the unit we're starting with. The other unit in the fraction has to be the unit we're trying to get to. Then our job is to multiply by the fraction in such a way that feet get canceled out and inches come in. So this way we are going to multiply, by 12 inches over 1 foot, because we know when we multiply out, we are going to wind up with feet times inches divided by feet, which means that the feet cancel out. So again, in dimensional analysis, we always start with our original value. And because we want this to be a fraction for everything to line up, if it is just a regular number with no denominator, we put this number in a fraction over 1 to signify where the numerator and where the denominator are. Then we multiply by a conversion factor. And this conversion factor has to be a fraction, and the numerator and the denominator have to be equal to each other, but in two different units, like 12 inches is 1 foot, or 10 millimeters is 1 centimeter, or 60 minutes in 1 hour. We would put one over the other. Then we would decide between two different versions of the conversion factor, and we are going to use the one where the numerator has the unit that we want and the denominator has the unit that we're trying to cancel. Then we just go through and do our math the same way that we always do math. Multiply across the top, multiply across the bottom, simplify by dividing. And then we are going to do the math on a calculator. Remember, if you're watching these videos are not meant for you to just watch and listen. If you're in my class, you should have a handout that matches this. You should be going along in your handout as if you were in class. If you don't have the handout, then you should have a piece of paper preferably a notebook handy, and you should be doing your math along with me. So I'll wait, you do the math with me. And the answer comes out to, sorry about that. Try that again. And the answer comes out to 81.6 inches. We always write down our units whenever we're doing this kind of conversion. So in this next one, we want to take an iron sample that has a mass of 4.5 pounds and convert it into grams. Now we have a conversion for pounds to kilograms and then kilograms to grams. So that means we're going to need to use 2 steps in this one. So to go from pounds to kilograms, we need to multiply by either 1 kilogram over 2.2046 pounds or 2.2046 pounds over 1 kilogram. Because remember, we want to multiply by a fraction. We're going to call this fraction a conversion factor, where the numerator and the denominator are equal to each other, but in different units. So really, we're multiplying by a fraction that equals 1. We're not changing the magnitude or the size of the measurement. We are just changing the numbers associated because we're using a new unit, okay? We're not actually calculating a change in amount. We are just changing the unit that goes with this amount. So for my first conversion factor here, again, I want to multiply, I want to put this over 1 to make it a fraction. And then I want to multiply by kilograms over pounds, because that will allow me to cancel out the pounds. Now, if I were to do this math, my answer would come out in kilograms. So now my unit is kilograms. Now I need to either multiply by 1,000 grams. Oops, that's 100. I either need to multiply by 1,000 grams over 1 kilogram or 1 kilogram over 1,000 grams. I need to use the factor that will cancel out these kilograms, which means I need to use the conversion factor with kilograms in the denominator. So when I plug that in, I do 1,000 grams over 1 kilogram. And what this allows me to do, numerator to denominator, because we're multiplying, these will cancel out. So to get my answer, I will do 4.5 times 1 times 1,000 equals divided by 2.2046. That will give me my final answer. And because grams is the unit that has not been canceled out, that is the unit that goes, sorry about that, that is the unit that goes with my final answer. Now this particular one, it's written as 10 to the third. That's because if we look at significant figures, we started with 3 significant figures here. And so the other way that we could have written this answer is it would be 2,040 grams. I would not use a decimal at the end because this 4.50 only has 3 significant figures, which means that that's the number of significant figures my final answer can have. 0.465 grams of C6H12O6. Again, it's a number that's not a fraction, so we put it over 1. First thing we're always going to do is find the gram formula mass so that we can work there. So I'm going to wait for you. You know how to find a gram formula mass because you're going to do carbon times 6, hydrogen times 12, oxygen times 6. I'm going to wait. So you should have 72.06 plus 12.096 plus 96 and you should get that the molar mass is 180.156 grams. So now that's going to get us from grams to moles. Now this is moles of molecules. Once we're in moles, we are going to say that it is times 6.022 times 10 to the 23rd molecules per mole. And it is 6 plus 12 plus 6, 24 atoms for every one molecule. So here we have molecules canceling, we have moles canceling, and we have atoms as our final unit. And you should be doing this on your calculator. I'll wait. And when I do this on my calculator, I'm going to do 0.465 divided by 180.156 times 6.022 second comma 23 so that we don't make mistakes. Enter. Times 24, and I am going to get, and on my calculator, I got, sorry about that, I got 3.73 times 10 to the 22nd atoms. Remember that a mole is the number equal to the number of carbon atoms in exactly 12 grams of pure carbon 12. Carbon 12 is what we base our moles on. 1 mole of anything is going to have Avogadro's number of particles, which is 6.022 times 10 to the 23rd units. And 1 mole of carbon is 6.022 times 10 to the 23rd. Carbon atoms will be 12.01 grams. We also know that depending on what we're talking about, we have different mole equivalents. So neon, because it is a noble gas, it is a monatomic element. So our 6.022 times 10 to the 23rd is the number of atoms that are in the mole, whereas H2 is a diatomic element. So that's actually the number of molecules. And then there's actually 2 atoms for every molecule. Sodium chloride, which is ionic, we call it formula units. And then because it's an Na plus NaCl minus, it's actually 2 ions per formula unit for NaCl. For example, if we want to convert 3.92 grams of iron to atoms, so we're going to take this 3.92 grams. It's a number without a denominator, so we're going to put it over 1, and we're going to multiply by a fraction where the numerator and the denominator are equal to each other in different units. When it is just a single element, like iron, we're just going to look on the periodic table to find the mass in grams that's equal to 1 mole. So everybody find iron on the periodic table. Iron happens to be number 26. So we're going to multiply by 1 mole over 55.85 grams. That will give us moles, but we have one more step, and that's going to be Avogadro's number of atoms per mole. Now, moles are going to cancel. Our final answer will be in atoms, and it was already calculated. However, if you didn't already calculate it, you should be using your calculator. Oh, making myself bigger. I'm not trying to do that. Using your calculator to try to get that answer. So I'll wait. And once again, the answer comes out to 4.23 times 10 to the 22nd atoms of iron. So that's the end of this video on dimensional analysis and conversion practice. Please ask me any questions that you might have. Please also send me an email or a remind message if you need help with anything from this video. Thank you. See you soon.